Matter and change. We're going to be looking at today what is matter, what are its properties, and how can it undergo change. So what is matter? Hopefully from previous science courses, you already know that matter is just anything that takes up space and has mass, which is volume and mass. And remember that mass is the actual amount of substance that's there. It doesn't matter where you're at, mass is always the same. So we don't want to confuse that really with what we consider weight. Here um, on Earth, our weight is depends upon the gravitational pull that's here. And so our weight will change if we go to the moon or somewhere else, some other planet, and that has a different gravitational pull, our weight will change. So you need to get into the habit of referring to how much substance there is as mass. Okay, if we look at the types of matter, really we're going to start putting them into either pure substances or mixtures. Whenever we think of a pure substance, we're going to be looking at elements and compounds. And when we look at mixtures, we're going to be looking at homogeneous and heterogeneous mixtures. There are two main categories of properties. Physical properties, which is anything that's descriptive. So if I'm going to tell you that a physical property of my shirt is that it's pink, that's physical. That doesn't talk to us about what it chemically can do. A chemical property then is going to give us example, like a chemical property of my shirt is that it's flammable. I know it's made of cotton, and so it will catch fire. If we look at physical properties and things that actually depend on how much of the substance is there, then that's going to be an intensive property. An intensive property is like mass or volume, because the more substance that I have, then the greater mass I'm going to have. The more of the substance I have, the greater volume it's going to have, or it's going to take up more space. The second type is intensive, and this is when you're not concerned with how much is there, but the type of matter it is. So I could take my shirt and put it on a balance and find out its mass, and that would be an extensive property. Or I can talk about that it's cotton, and then that depends on what it's made of. So it tells me um, an intensive thing then would be like perhaps its texture, because that's going to depend on what the type of material is, not just how much there is. The states of matter, like solid, liquid, gas, and we also have plasma and Bose-Einstein, but we're going to focus just looking at solid, liquid, and gas because we're just looking at properties. And whenever you give what state it's in, you're giving a physical property. Okay, so we can look at, based on their definitions, how do we categorize them? Well, one is going to be on its volume. Is the volume definite? Does it have a volume that if I pick it up from one off the table and I put it in a bowl, does it change the space that it's taking up? Does it spread out, or does it keep that same space covered? Solid and liquid are both definite. A solid, we know if I have a rubber band and it's sitting on the table and I pick it up and I drop it on the floor, it's going to keep the same volume. A liquid is the same way. If I have a 2-liter bottle of soda and I open it and turn it over and dump it all out on the floor, there's still 2 liters of soda on the floor. So that's what it means by a definite volume. For a gas, it's not definite because if I have a helium balloon and I pop it, the gas doesn't stay right there in the shape of that balloon and doesn't occupy any more volume. It spreads out until the next barrier stops it. So it's going to have a volume that changes depending upon its container. Shape is going to be the same, the same thing. If I have a table and I move it from one room to the other, it's not going to change its shape. A liquid, on the other hand, though, is going to change its shape. When I dumped out my 2-liter bottle of soda on the floor, it didn't pile on the floor back into the shape of that bottle. It now spreads out into a puddle shape, and so it doesn't keep the same shape. So it is not a definite shape. And just like we said about the helium balloon, how if you pop it, it doesn't keep the shape of the balloon, it spreads out as far as it can. So it's going to take the shape of whatever container it's in. If there's a temperature increase in a solid, even though you can't see a lot of it, there will be some expansion. Perhaps you've noticed as you've driven over bridges, there are plates where sections of the concrete come together, so that way when it expands and contracts, that will allow for some give, and not you won't have so many um, bulges and breaks in the concrete then. Liquid, because it has a definite volume also, is only going to have a small expansion with temperature increase. You will see a minimum amount of increase, but it has a definite volume, so it's going to keep its shape, just as a solid does. Gases, on the other hand, are going to spread out as till a barrier stops it. So the more energy you put into it, which is its kinetic energy, which is temperature, the movement of the molecules, that is going to allow for those gas particles to move further and faster, and they are going to expand greatly. So if you were to actually record the volume of a balloon on a cold day and you're outside, it's going to be less than what it is when you come inside and you measure it, where you've got the heat on, and inside the temperature's, about 70 degrees, where outside it's only about 5 degrees. So you have to kind of look at it and see where our temperature um, is at, and to be able to know how the gas is going to react. And that's because the gas does not have a definite shape or volume. So because of that, it allows it to have a large amount of expansion. So if they can express, can they be compressed? Again, with solid and liquid, because that volume is definite, you are not going to be able to put more in a space. You cannot push it all together and make it take up less space. But with a gas, you can. And that we use that property as far as filling tanks and different things with the gases, like an oxygen tank or a helium tank. Phase changes such as going from a solid to a liquid or a liquid to a gas, those are going to be dependent upon um, how much energy the particles have. We know that if I take a piece of ice and I put it on the table and I allow it to melt, it becomes a liquid. So that's my phase change. Then if I still leave that ice cube that melted on the table, it eventually is going to disappear. And at that point in time, we know we call that evaporation. If you've ever had a cold drink and you've been outside in the summer, then you notice that the cup becomes wet on the outside, and that we say like the glass is sweating. Well, the liquid's not coming from the inside of the cup. If it is, you probably need to get a different cup. But what's happening is that gas in the air on the outside, that water vapor that's there, is going to condense or slow down and lose energy as it gets close to that cooler substance, like that iced tea that you have. And so it's going to become a liquid and condense on the outside. So that's when we're talking about like if the glass is sweating or if there's dew on the ground outside. That's condensation. Then whenever we take a liquid and it becomes a solid, this is freezing, or you may also hear it called solidification. We have a tendency to think freeze is cold, but we have many things like gold and silver that are solids at room temperature. So for them to freeze or become a solid doesn't necessarily mean it has to be cold. It just has to be cooler than its freezing point. All of our phase changes then are considered physical changes, because if I take my ice cube, it is water, and I put it on the counter and it becomes liquid, it is still water. And then if it evaporates, it's still water. There is no change in its physical makeup. So examples we said are any of our phase changes. Other things are if I rip a piece of paper, if I crush up a sugar cube, it's still sugar. If I drop a glass and it breaks, it's still the same makeup. That glass is still the same. I've just changed its shape or its appearance. A chemical change, that's when you are actually going to form a new substance. So if I take water and I run an electric current into it, then it will separate into hydrogen and oxygen. So I have made a chemical change. I have made a new substance. It's no longer water. It is now separated hydrogen gas and oxygen gas. Anything that's mixed together is a physical change. It's simply just putting things together. It doesn't have a definite composition like water is H2O. There are always two hydrogen to one oxygen, so that substance has, a definite composition. With a mixture, it varies. If you've ever opened a box of Lucky Charms cereal and you pour out some of the cereal and you notice, wow, I have tons of marshmallows in this. Then the next time you pour it out, then to the next bowl, you're like, I don't have any marshmallows. That means that it's going to have a variable composition. That's what makes it just a mixture and not a compound. Two basic types are the heterogeneous mixture, which means that you can actually see a difference. So hetero means different, and genius means makeup. So it has a different makeup. Things that you can think of that are um, heterogeneous mixtures are like chocolate chip cookies, gravel, soil, a salad. If you've ever seen like Italian dressing that you can see the spices in it and you shake it up and then you use it, that is a heterogeneous mixture because I can see a difference in the makeup. The second type of mixture is a homogeneous mixture. A homogeneous mixture means that the composition throughout looks the same. An example of this would be Kool-Aid or air. Whenever I look at those, if I make a picture of Kool-Aid and then I fill up everybody's cup and everybody looks at it, it's going to look the same. It's not going to be uh, different from one to the next. They're going to look pretty uniform. So homo means same and genius means makeup. A key part about a mixture is that whatever is in it keeps its properties. So if I look at Kool-Aid, I know that it is a homogeneous mixture, and in this case, we call when something's dissolved in another substance, we call it a solution. And this one, I said we're going to use Kool-Aid as our example, but it could be like a brass instrument. So we've got two solids that were melted and then mixed together and are, and then are still there. And then you can think of, you know, just air. There you've got a gas and a gas. And we used Kool-Aid. We've got sugar and the powder, Kool-Aid powder in water. So there's a solid and a liquid. Your cars use antifreeze. That's a liquid in a liquid. And then you can look at water vapor that's in the air, just knowing that it's present and that it can condense at any time. That's where we can look at a liquid and a gas, especially if you look at fog. Okay, there we've got a definite high amount of liquid that's in the gas, and that's what we're seeing when we're looking at fog. So with our solutions, we said they will keep their same properties. So if I go back to what I was talking about and say, let's look at our Kool-Aid. Okay, I know that there's the Kool-Aid powder, there's sugar crystals, and it's all dissolved in water. If I put that in a pan and put it on the stove and bring it to the boiling point of water, then the water is going to evaporate. Now, the sugar and the Kool-Aid powder are not going to evaporate because they both turn to a gas at a much higher temperature. I'm only at 100 degrees Celsius, so therefore I'm only going to be moving what can make the change at that time. And the only substance in that mixture that can do that is water. And it's still water. It's just not mixed with the sugar and the powder any longer. It now has escaped and has become a gas and is water vapor in the air. So we have to know that their properties are going to stay the same. So now when we look at our pure substances versus our mixtures, we're going to be looking at elements. Okay? When we look at an element, we're talking about the atom. So there's only one kind of atom there, and this is the simplest kind of matter that has its properties. Anything below an element, then you are going into the parts of the atom. So we're looking at the smallest part of a substance that can have its properties, and that is the element, which is then we talk about it in terms of its atoms. So Breaking it down would mean splitting the atom. There's nothing physical that we can do to this to break it apart, where we were able just to separate the cereal or the Kool-Aid or anything like that. The second type of pure substance is a compound. A compound does contain two or more things that are in it, but they are chemically combined, meaning that their composition has been altered and changed. They are no longer the same. If we look back at water and we look at hydrogen by itself, it's a very um, flammable gas. If we look at oxygen, oxygen is extremely flammable also. Whenever I put these two together and chemically combine them and produce water, then I have the substance that our firemen use to put out most of the fires. So I have taken two extremely flammable substances and put them together and created a new substance that has a definite composition, cannot be separated physically, but has completely different properties now. That is a compound. So where we talk about elements, we talk about the atom. For a compound, we're going to refer to those as molecules. They can also be referred to as formula units. So when we start talking about different types of um, compounds, then we'll make a distinction between formula units and molecules. But in general, when you read through books and things, compounds are always referred to as molecules. So both a compound and a mixture can contain more than one thing, but the key is a compound is a molecule chemically combined. And mixtures can have compounds like water mixed with other compounds like sugar, or you can have um, an element mixed in with a compound. So it can be either molecules or atoms just put together in a mixture. How we separate them is very key, that to know the difference between them. Physical change for mixtures, chemical change for compound. And their composition, as we said, it's a definite composition for the compound, like H2O, and then for a mixture, it can vary, because we said, going back to think about the Lucky Charms, pour out 5 bowls. One may have tons of marshmallows, one may not have any, and one is somewhere in the middle. So it's not always the same proportions of the substances that are there. So if I look at this picture and I can see there's only one substance there, so this is going to be an element or atoms. Here, if I look, this represents things hooked together. So I have my pink molecule is connected with two yellow molecules, and every time it's the exact same composition. So that's going to be a compound. Then here, I notice that my two different molecules, or in this case, they're atoms, the yellow atom and the pink atom are not chemically combined together. They are separate from each other. So I know here I have a mixture of atoms. For our elements, we use chemical symbols instead of writing out the whole name, because when we start getting into chemical reactions, it would be very lengthy to keep writing out all the names. We have there are well over 100 elements. You would actually have to get on and like go to Harvard or somebody who's working on the project to see um, what the largest element is, to know exactly how many elements we have currently. Um, but we're not going to memorize all of them. We're going to be looking at the common ones that we use. So just know, though, the fact is there are a lot more elements than just the ones we're going to be using in class. The periodic table of elements shows them to you. Um, and just depending on how updated it is, it will show you how many, how many elements there are. The symbols will be one or two letters, and the first letter is always capitalized. And then the second letter is never capitalized. And you're always going to write in print. So you have to go back to kindergarten and remember your printing skills. You do not write chemical symbols in cursive. So you have to go back and retrain yourself just to print letters. Some of the symbols may not make sense, like tungsten, its symbol is W, but that's because it's from a different language, and the name of tungsten, that is that little filament in a light bulb that allows the electricity to run on it to light up, that we call tungsten in other countries is called wolfram, and that's what it was originally called and where it gets its symbol, capital W. Energy, the ability to do work, is what we're going to look at when it talks about chemical reactions and chemical changes. We're concerned about how much energy is transferred and how much energy is going to be required to make this happen. Really, everything is either kinetic energy or potential energy, meaning kinetic, it's in motion, or potential, it's in a position, or it's stored, it's not being currently used. So, but there are many types that you will hear referred to, other than just the kinetic and potential energy. You'll hear us talk about heat energy and chemical energy or electrical energy, mechanical energy. There are a lot of different categories of it, but really everything comes down to whether it's in motion or if it's not. Radiant energy, this again is just another one, and we'll look at the electromagnetic spectrum, and that's light. That's when we look at what can travel through empty space. So like the light from the sun, that is when well, we're looking at radiant energy. The law of conservation of energy is stated basically like the law of conservation of mass, where energy can neither be created or destroyed. It can just be moved from one type to another. So the energy just doesn't go away, it just becomes a different type. So where the sun has electromagnetic energy, it has light energy that's coming down, then that was formed from a nuclear reaction that happens on the sun through the fusion and fission of helium and hydrogen atoms. So from that nuclear energy turning into light energy, that then a plant will take in and turn into chemical energy to be able to create the energy that it needs to process the chemicals and to build its structure. So we've already talked about a chemical change. Just remember that at the beginning, whatever you are reacting, those are called your reactants. The stuff that you start with, those are your reactants. At the end, we produce something, so we call them the products. So a chemical reaction is always going to be written with what you start with and then show what is produced. A chemical change, remember, we know that the reactants will have different properties than the products because it is changed and it is not easily reversed. There's no physical way that you can just revert it back. So I can't just heat it up a little bit and separate it like we can Kool-Aid. Whenever there's a reaction taking place, I'm going to have some key things that show me a chemical reaction's taking place. One is there is a increase or decrease in temperature, and I'm not putting water on the stove and boiling it, but all of a sudden there are bubbles or gas being produced. There's a drastic color change, and I didn't walk up to it and paint it. It is if I take a piece of toast and I put it in the toaster, and then all of a sudden I see a gas being produced and smoke's coming out of the toaster, and I pull my bread, or once was bread, out of there and it's black. I now have a drastic color change, and so I know a chemical change has been occurring there. An odor change is because maybe I don't see a gas produced, but I can smell an odor. So that tells me there is a different gas that was produced in this. So it's just another way to identify a production of a gas. Then a precipitant. If I have a precipitate, this is when, if I take two solutions, two things that are dissolved in water, and I mix them together, and all of a sudden a solid is produced, then that means I've had a precipitate. The law of conservation of mass is what all of chemistry operates on. Our chemical reaction, the chemical equation, everything is to show that what I started with is still what I have. It's only been rearranged. When we talk about a nuclear reaction like the operation of the sun, then here we're dealing with energy equaling the mass of the substance times the speed of light squared. So if you know Einstein's formula, E equals mc squared, that's what you're talking about. The speed of light is a constant. All light on the electromagnetic spectrum travels at 3.0 times 10 to the 8th meters per second. So it's giving us an idea of how much velocity the substance has, and if you put that with its mass, then the energy that's going to be there is going to be different depending on the substance's mass and then the speed of light. In chemistry, again, the whole goal for us when we're looking to explain what we're doing is we're trying to find out what's happening. What happens with what we start with, those reactants, and what do we end up with? So the law of conservation of mass and the law of conservation of energy are the main driving points behind the chemistry course.